Hello, buddy. So today we're going to talk about groups, right? And so the notion is we're talking about the notion of a group, right? That's an issue of primary importance. But abstract algebra, as the name suggests, can get pretty abstract. So we're going to start with some simple examples. And the goal of these simple examples is to build up to this abstraction of this concept of what a group is, right? So let's begin step by step. Begin with a more geometric example. So consider the following square, right? So we have a square. We're going to label its vertices 1, 2, 3, 4. Right? We're going to perform a clockwise rotation to it. So we do a rotation there. Well, what do we have? We still have a square, of course. This is vertex 1, vertex 2, vertex 3, and vertex 4. Everything's just been shifted by 1 to the right. And then, well, if we rotate this clockwise, we have a similar thing again, right? So this becomes vertex 1, that's 2, that's 3, and that's 4. We do another one of these rotations, and now we have 1 over here, 2 comes there, 3 comes there, and 4 comes there. Suppose we do a fifth rotation. Well, if we do a fifth rotation, 1 comes there, right? Let's do a fifth rotation here. So this is now 1, that's now 2, that's 3, and that's 4. Well, notice that after doing a fifth rotation, this looks exactly like this. The vertices are in exactly the same place. So really, if we are to make a set consisting of the rotations, these kinds of rotations that you can do, well, our set consists of only these 4 elements, right? This one is extraneous, right? Only these 4 elements. Well, there's something really interesting about this set here that we just formed. For example, one thing you can note is that let's first label everything. So we're going to call this object of the set 1. We're going to call this object here R, meaning that this configuration or position was obtained by rotating the initial position once, rotating once clockwise. We're going to call this 2, R squared. It means we rotated twice to get to this position. I'm going to call this R cubed, which means we rotated 3 times to get to this position. I'm going to call this R to the 4. This position here, R to the 4, which means we rotated 4 times to get to the position. But as you can see, R to the 4 is just the same as the initial position. That is, R to the 4 equals to 1. In fact, things like, let's say, R to the 6, if you're to guess, what's R to the 6? Well, R to the 6 just means I rotate 6 times. But you see, when I rotate once, I get to R. I rotate twice, I get to R2. I rotate 3 times, I get to R3. I rotate 4 times, I go back to the initial position. I rotate 5 times, I go to R. I rotate 5 times, right? Actually, this is the 5th time, so I go to R. That is, R to the 6 really equals to R. Actually, I think we got ourselves a little confused here. So if I make one rotation, I'm at R. Second rotation, I'm at R squared. Third rotation, I'm at R cubed. The fourth rotation takes me to 1. The fifth rotation takes me to R. And the sixth rotation takes me to R squared. So R6 is really equal to R squared, right? So it doesn't matter what power we put over here, we can always loop back and give us an element on the set, right? And our set only consists of 4 elements, as we just saw, right? So I mean, notice something interesting about this. If we take any element of our set, say R and R cubed, 3 rotations and 2 rotations. Well, R times R cubed, we could think of this multiplication as meaning you rotate from the initial position 3 times and then you rotate once, right? So kind of like rotating 4 times, right? So R times R cubed gives me R to the 4, right? Let's try one more. Maybe R squared. R squared times R means I rotate once R by R. I rotate once, and then after that I rotate twice. So this is kind of like rotating 3 times, r cubed, right? Why is this so amazing, you say? Well, the reason it's amazing, or why we're so interested in this, is because what we're really discovering from here is that if I combine any two elements, right, notice that r to the 4, which equals to 1, is an element of our set. R cubed is an element of our set as well. Well, so what we're saying is if we combine two elements in this of this set using this operation of rotate then rotate, what we end up with is an element that's in the set. That is, you never leave the set when you combine any two elements. Another way of saying that is that our interesting set here is closed. Right? Closed. What does closed means? Well, closed means you can't get out. And in a sense, if you combine elements and they always stay in the set, it means they can't get out. And so you could think of this as being closed. This might be a new notion to you, so it's important to understand it, but we're going to repeat it a couple of times until it will make perfect sense. And it might not be immediately clear why is this closed thing so important, but we're going to find out about that. What else am I so interested in? What else is so interesting about this set, you might ask? Well, another important thing is consider the element 1, right? 1 corresponds to not rotating at all. Well, notice, if I don't rotate a given position at all, I remain with the same position. If I have this position and don't rotate, well, it remains the same. If I have this position and don't rotate, it remains the same. What I'm really saying is that, for example, r times 1 is really just the same as r. And r squared is really the same as r squared times 1. Right? So, what we're saying here is that 1 does nothing. 1 does nothing to any position. It leaves it exactly the same. Right? And so, we're going to call this element 1 the identity. Right? Identity just means you do nothing. Another important property is, well, we defined rotation to be clockwise, but no one stops us from going anti-clockwise. For example, suppose I rotate once and go to the position r. How do I go back to where I started? Well, I rotate backwards, yes, by r. And so we're going to define an element called r inverse. R inverse times r simply means that we rotate back. R inverse takes us back to where we came from. So r inverse times r gives us the identity. Right? R squared times, say, r to the minus 2. That is, you rotate counterclockwise twice. Well, r squared times r inverse r to the minus 2 still gives us 1. Right? So every element we see here actually has an inverse. Right? R cubed has r to the minus 3 as an inverse. Right? So this weird set we formed here has the strange property of having an inverse. Right? It has an inverse. And what else? One more thing we have here that's really interesting is, let's say I give you a couple of elements from the set, right? So I give you r, I give you r squared, and then maybe I give you r cubed, right? Natural question to ask is, do I combine these elements first, rotate 3 times, then rotate twice first, and then rotate my answer once? Or do I do this 2 first, rotate twice and rotate once, and then after that apply it to r cubed? That is, if I'm going to be more formal with you, we would write it this way, right? So remember that the brackets, as we might have studied in high school, reminds us what is the priority. Is this the order of operations, or must I do it this way first? Well, I need to erase this. I'm getting too excited and ahead of myself here. So let's erase this. Well, so, or is it this way instead, right? So that's the question we're asking ourselves. Am I going to multiply? Am I going to calculate this operation first and then r times that? Or am I going to do this first and then times r cubed? Right? Well, the thing to note about this particular set we created here, the set of rotations, is that this actually doesn't matter. It doesn't matter, as you suspected, possibly. It doesn't matter whether you do these 2 first or these 2 first, right? And you can actually verify that by carrying out the rotations yourself, right? Maybe a pictorial view would be, for example, this is kind of telling me, well, first you're gonna rotate twice, right? So 1, 2, then you're gonna rotate once, right? And then after that, after getting your answer, you're gonna rotate it 3 times. Well, that's 1, 2, 3. Okay, so it's kind of at the end you have 6 rotations. Well, how about here? This one is saying, well, rotate 3 times first, right? So we rotate 3 times, alright? Then we rotate twice, right? This was saying rotate twice, and then after that rotate once. So even pictorially, this and this right here and the bottom part, right? They look very similar, as you can tell. And so this is kind of like a pictorial demonstration, but obviously does not amount to a proof, right? So what I'd encourage you to do is to play around with a few of the elements over here to see that really it doesn't matter whether you start with this bracket or you work with that bracket, right? And if the bracketing doesn't matter, we say that the set is associative. So a set satisfies the probability of satisfies the condition of associativity, right? All right. Well, this is kind of curious. Let's analyze another set. Again, something you're very familiar with, very likely from elementary school. Well, the set of integers, right? And we're going to work with the operation of addition, right? Z is really the set of integers, in case the symbols are messing with you. So we have the set of integers right here. Well, we're considering things under addition. Well, I mean, let's say we have 2 plus 3. Well, we all know what the answer to that is, right? 2 plus 3 equals to 5. And then you ask yourself, why the heck am I getting so excited about this? The reason I'm excited is because 5 is also an integer, right? It seems to suggest something. If I get an integer a and add it to another integer b, whatever answer I get is always going to be an integer as well. And you probably know that this is true, right? So what is this telling me? Well, it's telling me that the integers under this property of addition have some special qualities. For example, the integers are closed under addition, right? Remember what closed means, just as we saw here. For example, here what we said closed meant was if you combine 2 elements, the answer you get is also an element of the set, right? R times R cubed gave us R to the 4, an element of the set, right? Here as well, that's exactly what we have, right? Is you combine any 2 integers and you always get an integer back. You can't combine 2 integers and get something that's not an integer. So in a sense then the integers are closed. You can't go outside. They're closed under this process of addition, right? Well, what other interesting property might we deduce from here? Well, let's consider the integer 0, right? 0 is definitely an integer. Well, we notice what we've known for a long time. 2 plus 0 would just give me 2. In a sense, 0 seems to be doing nothing to 2, right? And in general, any integer, a plus 0, still gives me that integer back, right? So this 0 does nothing to the integers. This is very reminiscent of our 1 over here. 1 corresponded to doing no rotation at all. If I don't rotate at any position, I remain at the same position, right? So kind of like I think we might have written it down here, like R times 1 equals to R, for example. So 1 is doing nothing, right? So in that sense, 0 is behaving like 1 from our set of rotations. And so we say that the set of integers has this weird property as well. It has something we could think of as the identity. In this case, the identity is not 1 but the number 0, right? It does nothing to the set. Well, what else might we deduce from here? Well, if I start from 0, right? Okay, so this is our number line, very familiar. If I start from 0 and go to a, right? I move a units all the way to from 0 to a. Well, the inverse kind of corresponds to undoing what I did with a. That is moving backwards. So I move backwards in this direction, right? That would be kind of minus a, moving backwards, right? That is a plus minus a takes me to the original position where I came from. So every element has an inverse. The inverse of 2, for example, would be minus 2. 2 plus minus 2 takes me to where I began, the origin, right? And so here we have the notion of inverse, right? Every integer has an inverse under addition, the negative, right? And this is of course very similar to what we saw again here with our set of rotations. If I rotate once, then R inverse refers to rotating in the opposite direction, counterclockwise in this case, right? All right. So this is curious. Let's do something else here. So consider 2 plus 3 plus 5, say. You must have asked yourself this question in elementary school. Am I going to add 3 plus 5 and then add my answer to 2? Or am I going to add 2 plus 3 and then add my answer to 5? Right? It could be very confusing which one to do. Right? And your teacher must have told you that it really doesn't matter which one you do. So you could add 3 plus 5 and then add your answer to 2. Or you could add 2 plus 3 and then add your answer to 5. Right? Which one you end up doing is really not that relevant. It doesn't matter. The answer is still the same. Right? So this is really the property of associativity, right? Reminds us of kind of what we're talking about here is, should I evaluate this bracket first and then product with R cubed, or should I evaluate this bracket first and then product with R? It really doesn't matter which one you do, right? So this set here is satisfying an interesting property, something we call associativity, right there. Okay. Let's evaluate one more group for funsies. How about that? Alright, so let's evaluate the set Q. And if you've forgotten, Q is really just the rational numbers. But we're going to evaluate the rational numbers without 0. You might ask me, why are we so worried about, why do we want to exclude 0 from the set of rationals? You'll see why that is important. So we're going to look at the rationals under the property of multiplication, otherwise known as dot, right? So let's see how this works. Well, notice, if let's say I get a third, that's a rational number that's not 0. I multiply it by, let's say, 2/4, right? Otherwise known as a half. What the heck? What I end up with is, as we all know, 2/12, right? And I could simplify it, I don't need to. Well, then you'll be like, Christian, why are you getting so excited about this? Why do we care so much? I know this already. That's for sure. Why I'm excited is really about the answer. And not that I got the answer right, but that the answer is actually a rational number, right? So you know very well that if I get a non-zero rational number A and multiply it by another non-zero rational number B, the answer I get is still a rational number that's non-zero, right? So in a sense then, the rational numbers without 0 under our operation of multiplication, right, satisfy closure. It's closed. That is, when you multiply two rational numbers, you never get something that's outside of the rationals. You always stay within. You're closed. You can't go out, right? Again, this is very reminiscent of what we've been seeing under addition here. Under addition, we said you get any two integers, A and B, you add them up, you get another integer. The integers were closed under addition, right? When it came to our set of rotations, right, what we talked about was if you combine two elements, let's say you rotate twice, then you rotate once, the outcome is also something that's within our set, right? So we are closed under, the set of rotations is closed under this operation of dot, right? Combining rotations, right? And so similarly, our set of rationals without 0 seems to be satisfying closure as well. Let's see what else it satisfies. Well, notice, if I get a rational number like, let's say, a third, right? A third. I multiply a third by 1, and my outcome is going to be a third, right? So 1 does nothing to a third. A third times 1 is 1, right? And so, and it's really true for any rational. If you get a rational number multiplied by 1, the outcome you get is still going to be that rational number. So 1 does nothing to the rationals, right? And that's the property of identity again. The set of rationals, right? The set of rationals has an identity element. Forgive my pen, so it always misbehaves, but the set of rationals has an identity. In this case, it's the number 1, right? We saw that the set of integers has an identity as well. We saw that. And the set of integers had the identity 0, because 0 does nothing to a, right? A plus 0 is just the same as a. When we looked at rotations, we had this element 1, the identity, which corresponds to doing no rotation. If I do no rotation, I remain in the same place, right? And so we are seeing that this weird identity is also in the rationals. In this case, it's the number 1, right? Well, what else do we have? Well, another interesting thing is that, as you must have learned before, is, for example, the number 2/3. I can multiply 2/3 by 3/2, thereby ending up with 1, right? And so 3/2 is the inverse of 2/3. It takes me back to 1, the identity, right? And in general, any rational numbers, you must know, when you multiply it by 1 over that rational number, always gives you back 1, the identity, right? So you could think of 1 over a as the inverse of a, right? And so here's why it's important that we excluded 0, because think about it. Which number are you going to multiply by 0 to get 1, right? Right? No such number exists. This is a question mark. We do not have such a number. And that's why we excluded 0. Because when we take away 0, suddenly everything has an inverse. And so this set that we formed, rationals without 0, has an inverse. The inverse property exists, right? So again, very reminiscent to what we were doing with the integers. We said that if you get an integer a and you add it to this element minus a, its inverse, you get 0 back. It takes you back to the identity. For example, 2 had an inverse of minus 2. 2 plus minus 2 gave me 0, right? When we're talking about the set of rotations, the inverse corresponded to going backwards to the identity. I rotate twice, and r to the minus 2 takes me backwards, right? Backwards twice to the identity, right? So again, this curious property of invertibility seems to be in all of our sets. Well, now suppose I get 3 rational numbers, like a half. Multiply a half by, let's say, 3/4, and then multiply that by a fifth. Well, naturally you'd ask yourself, in what order should I perform the multiplication? Should I multiply these 2 first, and then multiply my answer by a fifth? Or should I instead multiply 3/4, right, say by a fifth, and then multiply my answer by a half, right? So as you probably learned before, it doesn't matter which order you do this, whether you do this bracket first or that bracket first, the result is the same. So these rationals without 0 also satisfy this interesting property called associativity, right? I hope at this point I've now piqued your curiosity, because we have things that look pretty different. The rationals are fractions, the integers are just integers. What else are they? This is a set of geometric objects, a square that's rotating, but they all have this curious property that they all satisfy these 4 conditions. They're all closed, they all have the identity, they have an inverse, and they're associative, right? And this precisely is what groups do. This is really what abstract algebra is, because abstract algebra takes things that you know and things that you don't know, things that look like they come from a different planet, and brings them together and shows you what they have in common. And this is precisely what these 3 things have in common, and many other objects, in fact, like the matrices form a group, the real numbers also satisfy these 4 properties. Well, having understood these special examples, let's actually define what a group is, right? Let's get formal, because this is math after all, and in math we don't really, the special case is nice, but we want to be as abstract as possible. So let's be general, right? Let's define something generally. What we're saying is, if you have a set G and you have a property, we're going to call it dot multiplication. Well, we call this a group if it satisfies properties. Property 1 is closure. That is, if you take two elements, G1 say, and G2, these elements belong to the group. If you take these two elements and you multiply them with each other, well, whatever answer you get must also belong to the set G. Whenever this happens, it means combining any elements under the operation of multiplication never goes outside, it stays inside. So this set G is said to be closed, and we saw a couple of examples of that, right? So that's closure. How would you talk about, let's say, the other thing we know for sure is that there must be an identity element, right? That is, there exists some element E in G, such that for any G in G, right, any little g in big G, any element in G, G times E is really the same as E times G, which equals to G. That is, this element E, our identity element, does nothing to group elements or elements in the set. They hit it from the left or from the right, you get that element back, right? The identity does nothing, and this is important. It must be an element of our set G. The other property we want to hold is we want there to always exist an inverse. If you get any element G of the group, there must exist some other element G inverse, so that G times G inverse always takes me back to the beginning, the identity, and it must be from both sides. So notice that G times G inverse is not, in this case it is, right? So from both sides, G inverse times G and G times G inverse all give me E back, the identity. But in general, it's not. We'll see in general that it's not true that if you get two elements of a set, A times B does not always equal to B times A. But this is an aside, right? For the moment, just realize for inverses, the inverse can act from the right and the left, but regardless of which direction it acts from, the outcome is always the same. You go back to the identity right there. Okay. And the last property we've been talking about is associativity. And associativity just means it really doesn't matter how you the bracketing is irrelevant. So if you have A, B, C elements of the group of the set, we're not going to call it a group yet, let's just call it a set. Well, then it must be true that if you multiply these two first, then multiplied by C, your answer should be the same as if you had multiplied B by C first and then multiplied that by A, right? So it doesn't matter which bracketing you do first, right? And whenever these four conditions are satisfied, that is, you have a set that is closed, you have a set that has an identity, you have a set that has an inverse, you have this property of associativity. When these four properties hold for a non-empty set, it has to be non-empty. Whenever this holds for a non-empty set, then that set is said to be a group, right? And this is actually a very exciting principle, and it's amazing how much can be done from just these four properties, right? But one thing that's really amazing about it, I think I've mentioned it before, is it takes things that look so different and gives them something that they have in common. And when you work with this abstract notion of a group, sometimes what you prove for a group in general is going to apply to, say, a set of rotations, it's going to apply to a set of integers and addition, it's going to apply to the rationals, going to apply to matrices and all sorts of strange mathematical objects. So it's really a thing of beauty. And well, thanks for being with me. I'm gonna end this video. Hope to see you in the next one. Bye.